1.4 to, I believe, 1.6. And we are going to start here with the slide Managing Uncertainty, just to cover some of the concepts. So the ones that, the problems that in the notes say watch video for the answers are the problems that I'm going to do on this video. But I'm going to start with some of the slides beforehand to cover the concepts. And so when we are managing uncertainty, this is talking about different measuring devices. This is because when we're doing science, we're taking measurements. Everything is a measurement. We're representing the units of that measurement, but we also need to represent the uncertainty. So for an example, here is a piece of a graduated cylinder. If you've ever seen one, they're long and skinny, and you use it to measure liquid. Here, when we are reading this measurement, the liquid in here is going to form this curvature. And so the standard is to read from the bottom of the meniscus when we are taking a reading. And so here we're going to try to figure out what that number is. So we know that this is 35 and this is 40. And all of these lines in between are in between 30 and 40. So we have 1, 2, 3, 4 gradients in between that. So this is 36, 37, 38, 39, and 40. And so we're in between 36 right there and 37 right there. And so we're definitely 36 point something. We're not to 37. We're not at 36, we're in between 36 and 37. And so we're going to estimate how far in between it is. And so whoever's reading the measurement might have a different idea. Someone might say 36.5, someone might say it's a little higher than that, it's 36.6, some might say 36.4, some 36.5. So what we say is that these are the certain numbers. We know those for certain. And this one here is the uncertain or the estimated number. This is what we've estimated. How much uncertainty do we have? So when we're taking a measurement, the custom is to record all of the certain numbers plus the first uncertain or estimated number. So the previous example, it was 36.5. The uncertainty of the last number is usually assumed to be 36 or to be plus or minus 1 in the last uncertain digit. And so for here, it would be plus or minus 1 there. And so you would say that your actual range is 36.4 to 36.6. That's probably where your actual number lies, somewhere in between that. These recorded numbers are called significant figures. The number of significant figures is dependent on the uncertainty of the measuring device. Reporting a measurement to the number of significant figures is just as important as including the units. Reporting the volume of this as 36.5125 would be indicating a greater amount of accuracy than is allowed. So if somebody was said that they were able to read this number to be 36.5125, there is no way you could actually get all those numbers. No human eye could determine that. And so that would be lying if a scientist said this is the number that they got. That would be representing more certainty than they actually have. That would put the range of error here instead of here. And you want to accurately represent your range of error. So for example, the length of this pen, they measured it to 2.85 centimeters. And so the uncertain number is right there, 2.85. And if you look at how they measured it, here you've got 3, 2.5, so it's 2.6, 2.7, 2.8, and 2.9. So it's in between 2.8 and 2.9. And so here they blow that up, and so the human eye is going to have to kind of make up this system here and figure out where it is. And usually you can only kind of estimate that it's about halfway in between that. And so you would say 2.85, but you're guessing on this number. That's your uncertain number. So when we're counting significant figures in a number that we're just given, if you're given a number and you want to say how many significant figures or accurate numbers do you have, non-zero numbers are always significant. So these are easy. Anything with just non-zero numbers, everything is significant. Trickier is the zeros. And so here we're going to look at three classes of zeros. The first is what we call leading zeros. Leading zeros are to the left of non-zero digits, and they never count as significant figures. So 0.0025 has only two significant figures because these zeros are leading zeros. They're only placeholders. Placeholders, they tell us how big or small a number is. They don't tell us anything about the accuracy. So there's a big difference between 25 and 0.0025. Those zeros are important, but they are not significant figures as far as the measuring device is considered. Captive zeros, those fall between non-zero digits, and they always count as significant figures. And so these zeros here are significant. They're between non-zero digits. This has four significant figures. Trailing zeros to the right of non-zero digits are only significant if there is a decimal point. So 100, if you see the number 100, there is no decimal. These zeros are just placeholder zeros, just to tell you how big the number is, that it's 100 and it's not 1. There is a big difference between those numbers, but that's not telling you anything about certainty. And so what this tells you is that your last or your uncertain digit is the 1 right there. And so it's always plus or minus 1 in the uncertain digit, and so your actual range here is between 0 and 200, plus or minus 1 in that uncertain digit. If you put a decimal here, then all of a sudden your uncertain digit is right there. And so this has three significant figures. We can now count those as significant figures, and therefore your range of error is now, because it's there, it is 99 to 101. So it's a much smaller range of error. These here are your range of error. 100.0 has four significant figures because this decimal makes everything significant. Now your uncertain digit is there, and so now your number is somewhere between 99.9 and 100.1. So this gives you a lot more detail about the accuracy of the actual number because you have more certainty there. And so here it goes from being just a placeholder to having these zeros actually be significant. When we're talking about numbers, if we have an exact number, that is something that's not a measurement. It's either by counting or by definition, and it can be assumed to have unlimited number of significant figures. And so if we had 3 apples, that means I counted 1, 2, 3 apples. There's no uncertainty in that, and so it's an unlimited number of significant figures. It's not going to limit us when doing calculations. The same with a definition like 1 inch equals 2.54. We can assume that's unlimited significant figures, and therefore it doesn't limit us in calculations, which will be more obvious when we're actually doing calculations. So for practice, this is what you want to fill in on your notes. Here we want to figure out how many significant figures we have. So here we have 1.005. These are captive zeros. They are significant always because they're in between two non-zero digits, and so we have 4 significant figures. Here we have 35, and then we have these 4 zeros with no decimal place. Therefore, these are just placeholders, and they are not significant. And so we just have these 2 significant figures. Here, right here is our uncertain number. If you add a decimal, that makes all of this significant and this, because these are trailing zeros. And so now it's 1, 2, 3, 4, 5, 6, 7 significant figures. Your uncertainty lies in that number. And so there your range of error is much, much smaller. Scientific notation is a great way of hiding placeholder zeros. And so here we can put times 10 to the 7. That tells us how big this number is. But here we can put 3 and then 0.0. That's your significant zero. And so this is 2 significant figures. These are not significant. They're hidden in that scientific notation. And so when we talk later about calculations, this will be really helpful when we're trying to manipulate numbers. Here we have a captive zero, and then we have a trailing zero with no decimal. So it's just these that are significant, so 4. Here we have leading zeros, trailing zeros. Leading zeros are never significant, even if there's a decimal, so those aren't significant. Trailing zeros are significant if there is a decimal, and so these are significant. It's 1, 2, 3. This is where your uncertainty lies. This doesn't tell you anything about how big the number is. It would be the same size number if it was 0.05 as if it was 0.0500. Those are just there to reflect the accuracy of the measuring device. Here, 25.002. These are captive zeros, so 1, 2, 3, 4, 5. 5 significant figures. When we're calculating with significant figures, multiplication or division, you're going to take the smallest number of significant figures. So here, 5.00 times 6.0, you're going to want 2 significant figures because that's our least number of significant figures. Here you can see it's a little tricky because you get an answer of 30. But we can't just write 30 because we actually want to increase the number of significant figures. This is only 1 significant figure. And so you can add a decimal here. Sometimes though that won't work and you need to put it in scientific notation. And there's some practice problems that we'll work on that shortly. Here, when we get this answer, 2 significant figures. And so we're going to cut that off to 2, get 1.3. Here we have a really accurate number, a lot of significant figures. We're limited by this one though. So this shows you how when you're doing measurements in a lab, you want everything to be an accurate measuring device or you lose all the accuracy of your other ones. Here, we get this long number, we have to cut it off to 7. Addition or subtraction is different. Here you're going to be limited by the smallest number of decimal places past the decimal. And so the easiest way to do this is when you're adding things to line them up by the decimal, you're going to cut it off the least number of decimal places there. You can also just throw this in your calculator, look at the places past the decimal. This is 1 place past the decimal, so you cut it off there. Either one works. But you can see you get this number, you cut it off to 1 place past the decimal. For rounding, if the digit to be removed is less than 5, preceding digit stays the same. So here, if we were cutting it off right here, it would round to 1.3. If it's equal to or greater than 5, it's increased by 1. And so here, if we're cutting this off and rounding it, that becomes 1.4. But this one and this one here rounds to 3.2. 1.89 rounds to 1.9. And then here, if you're going to cut this off, this 9 bumps up that 9 to a 10, which bumps up that to a 2. You get 2.0. Here, let's do some calculations with significant figures. Here we're going to want the least number of decimal places. So we will do all the adding here. 7.932, but I want to cut it off right there. 7.9, one place past the decimal. Here I'm going to line everything up. 21, 13.8, 130.36. This is where we're going to be cutting it off. I got 6, 6, and then 1. And so here, 0 places past the decimal is what we're limited to, and so we get 165. Here we have 2 significant figures and 3 significant figures. And so we get 7.222, but we cut this off to 2 significant figures and we get 7.2. Here we're first going to do multiplication. Gives us 3.724, and then we're going to add that to 8.41. And so I'm going to do 3.724 plus, but first I'm going to cut it off to 2 significant figures. So here I get 3.7, and then I add that to 8.41. I'm going to cut it off to the least number of decimal places. So I get 12.11, round that to 12.1. So why is this important? Here's an example of why it could be. So say that if anything greater than 1.50 grams of a certain material is hazardous to your health, what is the significance of knowing that a certain sample has 1.000 grams of this material versus 1 gram of the material? 1.000 grams, that means that here is your uncertain digit. 1 gram tells you that here is your uncertain digit. So look at our range of error here. Here we know the number, the actual number in this sample is between 0.999 and 1.001 grams of hazardous material. And so here you're safe. You know it's not 1.5. If it's 1 gram, that means it's plus or minus 1 in the uncertain digit right there. So it's between 0 and 2 grams of hazardous material. You are not safe then. It could be 1.5. And so therefore, if somebody got this measurement and it was just 1 grams, then this would not be a good number. So say somebody got this number and there were actually this number of significant figures, but they just represented, they just didn't add those zeros, they just wrote down 1 gram. This is why it would be important to say 1.000 gram. Could be a life or death situation in this case. Here are some practice problems that we can, when we're calculating with significant figures, we get an answer and we have to represent it to a certain number of significant figures. It can sometimes be tricky to manipulate it. And so I like to go over some of the trickier examples just to help you know what you do in that situation. For example, 600,000, we want 3 significant figures. And so here we could, if we left it like that, it's 1 significant figure. If we added a decimal, that's 1, 2, 3, 4, 5, 6 significant figures. And so we're at a loss to know how to do it. This is where scientific notation is really helpful. Because what you can do is put all those placeholders into scientific notation. So I can write this as 6 times 10 to the 1, 2, 3, 4, 5. 10 to the 5. Then I want 3 significant figures, and so all I have to do is add a decimal point, and then any zeros I add will be significant. They won't change the number because the number is held in that times 10 to the 5. These zeros only add certainty, and so this would be our answer. Here, 557.59 to 1 significant figure. So that looks weird. How are we going to make that one significant figure. Sometimes people are tempted to make that 6. It's not 6. This is closer to 600 than it is 6. We need to reflect how big the number is. So put it in scientific notation. Even though this is a weird number to put in scientific notation, go ahead and do it. Go back 2 places and we get 5.5759 times 10 to the 2. Now that tells us how big our number is. Now let's cut it off right there. The 5 rounds up the 5 and we get 6 times 10 to the 2. If you're able to see this and say, oh, that would be 600, that's fine. Go ahead and do that. But it can be hard to see that at first, and so scientific notation is really helpful. 720 to 5 significant figures. This is an easier number because all we have to do is add a decimal. That makes us 3 significant figures. Any numbers we add now, just add significant figures. They don't change the number, it's still 720, but here are uncertainties right there instead of way back there. Here, 0.0089 to 4 significant figures, it's the same case, where if we add decimal or zeros here, it's not going to change the size of the number. And so I can just go ahead and put 2 zeros. You could also have done 1, 2, 3, written this as 8.9 times 10 to the negative 3, and then just add zeros right there, and that would be fine as well. 524 to 2 significant figures. And so here, if you see that, okay, I'll just make that 520, then that's fine. Or you could put it in scientific notation, do 5.24 times 10 to the 2, cut it off right there, 5.2 times 10 to the 2. Here to 3 significant figures, you can cut it off right there and not change the number. Or, so you could do 0.0209, or you could write this in scientific notation. 1, 2, we do 2.08689 times 10 to the negative 2, cut this off right there, 2.09 times 10 to the negative 2. Here, 4.99989 to 2 significant figures. We're cutting this off here. This 9 rounds up this 9 to a 10, which bumps up the 4 to a 5, and so we end up with 5.0 for our answer. Sometimes rounding can be a little tricky there, which is why I threw that one in there. Okay, so this concludes the section on significant figures. I will make another video with the next part of the notes for conversion factors and density.